Hi, we're now going to be looking at chapter 15. So let me try to contextualize for you where we're headed. This is called functions of several variables. I'll just point out that in chapter 4, we had functions where there was a single input and multiple outputs. So in chapter 4, the functions look like this. T comes in and a vector's worth of stuff, x, y, and z came out. That might be r of t. T is the input. I'm writing the components, x, y, and z of the output, but then later on we started thinking of that as a single entity, a vector. Well, what we're going to do in chapter 5 is essentially the reverse of this. We're going to have multi-inputs and a single output. So now, well, there's two things we'll do because we can't really go into the fourth dimension. We're going to do two inputs and a single output, and usually those will be x and y are the inputs and z is the output. The other thing we can do, which is, honestly, this does require you to think about the fourth dimension a little bit, but you can get away without having to do that too. Think of a function that has all three variables, x, y, and z, as the inputs, and something else, I don't know, q, as the output. So what kinds of entities are these? Functions that have multiple inputs and a single output. This is probably the easiest kind to understand. What that says is, at every point in the xy plane, you'll get a z coordinate. In other words, you'll get a surface that lies above the xy plane if you have a function like this. And we've actually seen some of these already. Suppose I gave you the function f of xy is, oh sorry, I should label this as an example, as x squared plus y squared. And then we plotted what is z set equal to f of xy. This is literally what I mean when the z is being set to the output of this function that takes two inputs. Well, yeah, that was one we looked at when we were dealing with quadric surfaces. The graph of it is a circularly, actually I guess I should draw that so that it looks like it passes behind the axis. A circularly symmetric paraboloid. Darn, I missed. Okay. I was going to try to shade it or something, but it's basically the graph you get if you take the y equals x squared, or sorry, z equals x squared, and rotate it around the z-axis. It's that shape. But this is the sort of thing we're talking about here. At any point in the xy plane, somewhere way up there, there's a point on this surface. So yeah, that's the idea, surfaces, where z is a function of x and y. Well, actually, not necessarily. You could do y is a function of x and z, or x is a function of y and z. You can make surfaces that are given by functions in more than one way. So this is one good way to get functions, but it's not the only way to get. Darn, I just said that wrong. This is one good way to get surfaces, but you don't necessarily have to have a functional relationship between the two inputs and the one output. For instance, you could have instead of a rocket nose cone, you could have a ball. I don't even want to try to put the axes on here, do I? It's just try to think of the shape of the Earth, right? That was the equator. I put some lines of latitude and everything. If you think about this as z equaling a function of x and y, you're going to get in trouble because imagine a vertical line. It's going to pierce the surface of the sphere somewhere and then come back out of the surface of the sphere later. And that means there are two different z coordinates that go with that xy pair. That's not a function. Now, admittedly, you could make this thing a function. If you just erase the southern hemisphere, now you've got something that's a function. And then you could make two functions, a new one now for the southern hemisphere, and sort of glue them together. But there's a better way to approach that, and we're going to see that by the end of this section. For visualization purposes, when we're dealing with surfaces, it's useful to think about cutting the surface at different heights. So you might have 1, 2, and 3 as heights on this z coordinates, right? And what would it look like if you sliced through that surface at those different heights? Well, you get something that kind of looked like, actually, you know what, this circle that I drew at the top is the slice at the height z. There's another circle back there at height 2, and then there's a really smallish circle here at height 1. Well, smaller than the other two. This leads to a great way of visualizing surfaces, which are known as contour plots. So I'm going to go over to the screencast setup and show you some virtual models to illustrate how contour plots can be really useful for sort of understanding what's going on with a surface. So this is a piece of software I use for designing things to be 3D printed. This particular surface that is shown here is, well, maybe it's hard to view it as being a surface first because it's been kind of blocked up, almost Minecraft-like. But it's used to illustrate the idea of contours. And the shape of this thing, I'll try to move it around a little bit to let you get an idea of how it's formed. It has 3 different places where it sort of goes downhill away from this central plateau. 2 one on the left side, 1 on the right side, and then 1 on the front of it. And then it has 3 different places where it goes up. And this surface is jokingly referred to as the monkey saddle, because, you know, if you were a monkey, having a saddle that's shaped for a human wouldn't leave a place for your tail, right? So, yeah. If you had a 3-legged, maybe Martian saddle would be a better name. You had some 3-legged person, they would need to have a saddle shaped like this. Although, you know, the other thing about a saddle is it literally fits to the shape on the back of a horse. So this thing would be rather uncomfortable for the horse. Get this part here that would dig into their neck. So yeah, the monkey saddle, it's cute, right? Now, the only problem with showing you the way, when you hold one of these physically in front of you, it's actually really easy to see the contours. But in the software here, if I try to look at it from dead above, the contours basically just disappear, which is unfortunate. If I hold it at a slight angle, you can sort of see the contours then. There's all these curves that are, there are places where the surface actually just has the same height. Now, there is another place where you've likely seen this. The other place you've likely seen this sort of thing is in a contour map. Well, I don't know if people will have seen these, but if you haven't, it's actually a very useful skill to develop. This is a site called How Stuff Works, which has a lot of good lessons on all kinds of crazy things, but they're basically giving an illustration here of how contour lines work. I've got a bigger view of that image right here. So the idea is this: you've actually got some 3-dimensional surface where z is a function of x, y. In this case, it's literally the surface of the planet we live on. They're showing the contour lines here, which if you're in 3D, what it means is that's a place where if you walked along that path, you wouldn't be changing your elevation. This is, if you're on a hillside and you walk dead sideways to the slant of the hill, you'll follow a path that neither goes up nor down. Those are the contour lines. So, and then this is typical. The contour lines are often labeled with, at least some of them are labeled. So, and then you can fill in between them. 100, and I guess that's 150, the other dark line, 200, 250, 300. Notice that there's No contours above 300. That's what happens when you have what's called a mesa, where there's a flat top on the thing. I think they didn't intend for this to end that way. It's just that they ran out of room. But if in fact you did have a map that showed a last contour line with nothing inside it, you know you've got a flat region on the top of the mountain. Couple of things are interesting to note when you're planning a hike or trying to do some climbing or something, and you've got a contour map like this. It's easy to tell where is the slant of the slope of the land large and where is it small from the contour. On here, I would say roughly where my cursor is here, where it actually labels contour interval. That's about as least of a slope as there is. Maybe up here is even more small. What you're looking for if you want to have a gentle slope to get to the top is contour lines that are far apart, because that means you go a fairly decent horizontal distance while you're rising, however many feet that is. Let's see, seem to have divided 100 feet up into 10 subintervals. So those contours are 10 feet vertically apart. If I go 10 feet horizontally and 10 feet vertically, that's really steep, but it's better than some of these other places. Like right in here, you see how close those contour lines are together? We're going from 250 to 300, which is an increase of 50 feet all told in a space of about 20 feet. That's quite steep. So yeah, that's a little something you can tell from contours, but you can also kind of get a feel for the lay of the land by looking at contours. This is a sample test. Actually, we'll be getting a sample test very shortly because we're getting close to that time ourselves. But from fall 2017, where there's a problem on here that I really enjoy. I think it's kind of a fun one. There's 4 graphs on the right, and then there's 4 sets of plots of contour lines on the left, and it's just a matching question. Now, one of them I think is pretty easy. These top 2 things must be the same. Do you see how you have this nice rounded dome of the top of a hill there? It would have contour lines going around it in concentric circles. So that one's not so bad. That one looks nutty, so let's skip that for a second. When would you get contour lines that look like that, where there's an X in the middle? Well, that turns out to be this kind of surface, a saddle surface. There's actually, it's a little hard to see, but there's a line going away from us that way that's pretty much all at the same height. And there's another line perpendicular or parallel across the plane from us. It's in the plane of that we're viewing things, and that would be more or less horizontal. That's those 2 things that cross at our necks. So that point in the center, it's called a saddle point. Actually, it's sort of an interesting location. Usually, if you're at a location on a surface, there's only one choice. You can go up or you can go down. Or maybe you can go sideways, but there's just one direction in which you could potentially go sideways without going up or down. There's some points where you have no choice like that. Like if you're at the top of one of these hills, there's no way to move without changing your altitude. But the generic thing is that if you're at a point, you've got one direction which will be sort of horizontal motion, and another direction which will go up or down. But at a saddle point, you have more choices. You've got 2 different places where you can, 2 different directions in which you can move without changing your altitude. It's kind of fun. If you don't believe this, go buy some Pringles chips. They're saddle shaped, and you can take a marker and draw on the surface of the potato chip, and see that there's 2 different lines that you can basically make straight lines across the Pringle chip that are yeah. Okay, weirdness. On this particular saddle surface, we've got to the left and to the right, we're going downward, and up and down. In the X direction, I suppose we're going upward. Y direction down, X direction up. But that contour matches with that guy. So we only have 2 things left. And this is, when you're in a testing situation, you want to use process of elimination. This one here, you can see it definitely just seems to have 2 bumps on it. And there's another contour down here that has 2 bumps on it. I guess there's getting ready to be another bump down low, a low spot here, but it It's off the edge of the screen, so we're not seeing that. So it must be this thing, which is supposed to look like the eyes on the owl, is matched with the third of the plots, which leaves this last one to be this thing. Now, this is a shape actually you see all the time in packaging. There's a lot of packaging that has this waffle shaped stuff that helps to absorb shocks if items are in transit. Often made out of recycled, like pulpy paper, so they're kind of cheap looking thing. The nice stuff is bubble wrap, but if sometimes you see cheap stuff where it's been shipped with this kind of waffle paper around it. Okay, so I guess that's good examples of contours. So I wanted to try to reproduce for you a picture that I remember seeing back when I was a little kid in one of these little books that they get for children about basic science. My parents used to get me those things, which may be why it turned out so bad. But this would be from the How and Why Wonder Book of the Earth. And it was trying to illustrate the interior bits of the Earth, and like the parts that you probably know, especially if you've seen the movie, the core is this thin layer of stuff that's right under the surface is called the crust. And then there's a layer inside of that, it's called the mantle. And then that part that's red because it's supposed to be really hot, that's the core. And this is typical of a lot of things that have spherical symmetry, that there are layers like this. The core is made out of nickel iron and it's molten. The mantle is mostly solid, but there's plenty of liquid stuff kind of in this. Yeah. That's where there's magma, right? And occasionally the magma from the mantle pokes out and goes through the crust and you get volcanoes. The reason I'm showing you this, though, is that it is a reasonably good example of level surfaces for a function that's in 3D. So that is, if we have the sort of functions where 3 inputs determine a single output, maybe x, y, and z are the inputs, and how about temperature, T, as the output? It's sort of unfortunate that maybe if I made it a capital T, it would be better choice. I don't want you to think of that as time, it's temperature. So the level surfaces of temperature are things like the boundary layer between the core and the mantle. That's at one temperature, and then where the mantle changes from mostly liquid to mostly solid, and you get the crust. That's another temperature layer. If you have surface, so if you look at what's akin to level curves in this setup, they're level surfaces. So yeah, the surface of the Earth, the bottom of the crust, the surface of the core. There's actually more out here, right? There's the atmosphere on the outside, and then there's oh gosh, what is the atmosphere? Got like 3 different layers in it: troposphere, stratosphere, ionosphere. There's layers beyond this, right? And then there's, even in space, there's more layers out, and they all have to do with, well, actually with changes in temperature. So that's not a bad model. The temperature is a great example of a sort of function that you can think about visually, where it's a function from 3 variables to 1. You just imagine that, like the room I'm in is full of tiny little thermometers dangling all over the place, right? Just in your mind's eye, you picture that, and each thermometer has a slightly different reading on it. But there would be a layer of things that are roughly the same temperature. It's probably the case, most of the time this is true. The cold air is down near the floor and the warm air is up near the ceiling. So you see a gradient or a change in temperature as you move around in the room. I actually remember seeing this, experiencing this very vividly as a kid. My dad, for a period of time, he'd been injured on the job, and so he was out of work for, 6 months or more. And he wasn't very happy about it. He'd sit at home all by himself and smoke furiously. And one day I came home from school, and there was this clear thermocline. You could see the air was clear from about 5 feet down, and then it was smoke from 5 feet up. It was kind of neat because you could see the dividing line between the cold air and the warm air in the room because of all the carcinogenic smoke that was in it. Another place I've seen that recently is I started learning to scuba dive, and the place I dove was a flooded quarry in Pennsylvania, and it's really remarkable. As you descend, the deepest you can go without special equipment is about 100 feet, a little over 100 feet. But as you descend, you feel these different layers of coldness in the water, because it's not like the ocean. It's not circulating a lot. It's just sitting still. And you know, there's very distinct layers of different temperatures in there. So those layers of different temperatures, those are level surfaces as opposed to level curves. And that's really what I'm trying to get you to visualize here. Level surfaces. And finally, I want to make a connection between these level surfaces and level curves and the functional approach and then the implicit approach to graphing things. So bear with me. We'll back up to 2D for a second. I might think about a function z equals a function of x and y, say. For instance, particularly x squared plus y squared, just to make it concrete. And the graph of that function is, well, it's something I drew before for you. It's an inverted paraboloid. So that's close enough, right? It looks like a nose cone going downward, and there's an interior to it too. Visible there. If I think about a level curve on that, it would be, well, let's say a level curve. It would be, for instance, x squared plus y squared equals 1. And the graph of that is no longer anything at all three-dimensional. It's two-dimensional. In fact, it's a circle with radius 1. And this graph, well, that's sort of your classic example of an implicitly defined graph. That is, this circle is not something you can graph with your graphing calculator, because it doesn't look like y equals f of x. It looks like a relationship between x and y with kind of no preference about one is bigger than the other. When you say y equals something, then it's like you think y is more important than x. Here, it's very democratic. X and y are being treated the same. We're just collecting all the points where the sum of the squares of the coordinates are 1. Well, if we do the same kind of thing in 3D, would be have a function of f. So the previous thing should have probably been headed 2D, but now we're definitely going to 3D. F of x, y, and z equals something. The graph of this is really in 4 dimensions. You have to have 3 dimensions for your input and a 4th dimension for your output. Which, you know, is pretty hard to see. It's pretty hard to visualize. If you do want to visualize it, you can imagine just putting a whole bunch of points all over the place in space and assigning numbers to each of them. 1, 2, and that was 2 as well. There's 3, and there's 5, and things like that. But the level curves, well, those are things we can see because they're in 3D. They would be things that look like f of x, y, and z equals some constant. Not really a variable, but a number on the right-hand side. We saw things like that. Like when I showed you all the quadric surfaces, they were of this form. Some expressions in terms of x, y, and z usually equal to 0 because we moved any constant to the other side. But this is an example of an implicitly defined surface. And if you're using Sage CoCalc, this is something you can easily plot. This is where the function implicit plot 3D gets used. When I was showing you guys the quadric surfaces, I think it's implicit plot underscore then plot 3D. I may be misremembering the name of the function there. But that's exactly, I'm not going to show the arguments to it, but that's exactly what this implicit plot function is for. When you don't have it solved as z equals some function of x and y, but just some relationship between x, y, and z that's equal to k, or you can also move the k to the other side and have something equal to 0. So if I give you a whole bunch of level curves, for instance, let's make this real with a function. Suppose we said f of x, y, and z was the sum of the squares. Well, again, the graph is really kind of hard to see. It's sort of a distribution of values through three-dimensional space. It would be 0 at the origin, it'd be 1 farther out, it'd be 2 after that. You know, it's, in fact, what I'm graphing here is the square of your distance from the origin. So yeah, it's calculable, but it's still kind of a question mark. But the level curves, darn it, really should have changed that word to surface when we moved to 3D. The level surface, well, can we think about what x squared plus y squared plus z squared equals to a constant is? Let's do just a particular number. How about 1? What's that level surface for our function? That's a sphere of radius 1. And it's easy to see that if you jump it up to some other value, x squared plus y squared plus z squared equals r. That will be a sphere. I guess I should write r squared. Yeah, that would be a sphere of, and I can't seem to spell. The level surfaces are concentric spheres of radius r. Here, I'm gonna fix this because I don't like doing that way. X squared plus y squared plus z squared equals to some constant. That's going to be a sphere of radius square root of k. Okay, and you can sort of imagine a lot about the graph of this function of 3 variables that's really impossible to picture by thinking about these level surfaces. Okay, spheres, and it's constant along those spheres, and it's getting bigger as we go out. That part makes perfect good sense to people. That brings us to the end of what we want to do in section 15.1. This will be posted, it's now about 6:30, so probably about 8 o'clock Tuesday night. Hope everybody gets a chance to see it before Wednesday morning, but the worksheet will cover this as well as a little bit of a review from the last one. You probably won't be in horrible shape if you, well, you're not even going to hear these words unless you finish the video. I'm going to sign off now. See ya.